So yes, so I will straight away go into the topic. Deepak has already given me a nice introduction, so I don't have to go there. So let me. Okay, I can minimize this. Okay, so the first of all, I would like to thank um, NIT Jaipur for inviting me for this talk. It's truly an honor to be presenting my work to some of the best students and faculty members in India. So with that, let me start my talk. So my talk will focus on interpretation of AI technologies in medical imaging, including conventional approaches, neural networks, CNNs, and also will look at aspects of the foundation models as well. So a quick recap of my work, and yeah, this is something Deepak has already summarized. I don't want to get into that, and just also want to let you know that I also have some entrepreneurial ambitions, and so I have consulted with different Indian startups in the Gen AI healthcare space and also in rural health, and also a co-founder of a stealth startup, which I mean, it's a Gen AI startup, but it's in stealth mode right now. Okay, so let's come back to our topic, which is deep interpretability in deep learning for medical image analysis. So this is a somewhat of a early statistics which shows that how the deep learning in medical imaging field has evolved over time, and starting from 20. So it really took off in 2015, 2016 after AlexNet and all, and then also there are but now if we look at the statistics, it's pretty high. But the trend is that yeah, there are more and more numbers. There are more and more um, researchers working in medical imaging, and this is something probably something very familiar, somewhat familiar to many of you. Is that how after the AlexNet was introduced for the ImageNet challenge, how things change, that completely changed the picture for AI and deep learning, particularly starting with computer vision, because at that point of time, the initial uh, computer vision was the main driver of the AI revolution. So right now we see in between there was like language technologies with GPT models or language models, LLMs, but now VLMs are getting into the mainstream. Then there are, of course, audio models, truly multimodal models. But the first revolution, or which happened, was in computer vision, and uh, so explainable AI techniques started to be when people started investigating, because the concept of explainability is not new. It's been there for a pretty long time, like starting from, let's say, decision trees. Decision tree is how do you come to a particular decision given an input and the output. So it would show the intermediate steps, like based on this particular parameter or value of a particular feature. This was the decision taken, like, tree comes, yes, no, branches off, then sub branches, and so forth. However, it is found that if you plot with explainability in the y-axis, you'll see a very interesting phenomena. The higher the accuracy, the lower is the explainability. So something like decision trees comes at a balance somewhere in the middle. Then Bayesian belief nets is lower on the explainability, but deep learning methods, they score very low on the explainability aspect. Although in terms of performance, they are definitely the state of the art. So, what is exactly is interpretability? So, of course, the concept of interpretability was that when you start using these models, ML models in different tasks, you don't know what you are getting into. So, I mean, what are the factors that led to this a particular decision? So that is something one must be aware of, particularly in critical areas like security or even financial transactions in healthcare. So the interpretability can be defined as is kind of a link between features used by the model and the prediction itself, and such that the things can be understood by the human. So if I were to say that output a list of numbers as interpretability, some kind of vector, that would not make any sense to me. But there should be some way that the humans can interpret that. So it can be like if you are using, for example, in random forests or decision trees, if you are using 50 features to model as a feature extractor, then uh, then a corresponding vector could be the importance of these features, which you get in a like a Gini index and all that. So that kind of numbers, those make sense, but not some any random. For example, logits, we can't make a lot of sense unless we transform them. So why do we need interpretability? Because with the popularity and of ML models and their being in the mainstream, so we need to know how it works and how can what are the factors it considers when it comes to a decision. So initially the Alan Turing Institute came up with these what we call the fast track principles: fairness, accountability, sustainability, transparency. So if you are somewhat familiar with the robust and responsible AI, then these terms make sense to you. But these were but the foundations were laid somewhat in I think 2017, 2018 during those times. And so this is particularly important because we want that ML models should we should be able to trust that it should there should be a quality control. It should not be like output random. If you change some little initial condition slightly, you don't want to get very different outputs. And also something that is very important nowadays is the ethical aspects. Like, are we taking the doing the training the models with the right kind of data, etc. And then so there were proper laws that were also started to be framed around interpretability and accountability. Because if let's say you are using your classification model in a diagnosis setup, and the model makes a wrong decision, then who is accountable for that? Who is to be held liable? Then who do you go to and talk about this? So that's when the European Union came up with these GDPR rules. And then people started. So initially the focus was on quality assurance by evaluating a model's performance, then ensuring robustness and knowledge of where the algorithm would break and what are its limitations and all that. And also important for to have trust, because as I said, critical fields like medicine or even security, defense, all these things, you need to have be able to trust the model. Particularly if you want to augment, for example, radiologists with additional AI tools, then you need to be able to trust the ML model. So then particularly in the context of healthcare, people started talking about how can we mathematically define these terms, which initially may seem vague. So how can you quantify whether it's trustworthy or not? And so a different kind of policy papers and different opinion papers started coming out. So in this talk, I will focus mostly on the image-based, the computer vision aspect, where and how do we interpret models that are applied to images. So these were some initial works that looked at different aspects, like even as early as 2015, there were a lot of work that was going on, and then these things, or even in healthcare, people found very unusual results. So we'll go into that one by one. So the first thing that came up was for CNNs was to get attention maps. Like if a image input image gives, if a model gives a particular output for a given input image, how do you know which areas was important? Because neural networks are basically the conceptual is that it fires, or rather it is activated at certain specific neurons get activated at certain locations of the image. So then try to back propagate and understand which are the regions. For example, in this image, if you say this was the original image, then there were what were the classes? Electric guitar, acoustic guitar, and the Labrador dog. But then it started focusing on these areas for the guitar, the acoustic guitar, and for the dog. So this worked out fine. And but if you were to look at this particular image, which was misclassified, this husky, it's a type of dog, of course. It was classified as a wolf. But when you look at the attention maps as to why, it started showing these regions, the back, the floor. It's not exactly the face of the dog. It looked at the ground. It probably interpreted it as a forest, and hence the animal is a wolf. It did not look at the fine grained features and all. And then in what happened is, again, in some cases, these clinical sites, different X-ray machines are marked by different symbols in the final outcome. So the neural network started learning those things instead of focusing on the actual image or the anatomy, the lungs, chest, whatever. So if we did not have these explainable methods, then we wouldn't know exactly what the network is learning. So likewise, so yeah, this is just a zoomed in version of that. It's just a marker that corresponds to the sites. So after this splash made by AlexNet and all that, and so they were kind of giving human level performance or beating humans in many cases. Like for example, in this case, classification, all the earlier CNNs, AlexNet, GoogleNet, VGG16, ResNet 50, they did as good or even better than humans. But if you give them original image, but if you give them grayscale image, also it was similar, not a significant difference in performance. But if you give only the silhouette, oh, that was really bad. It really showed the stark difference in performance between the humans and the algorithms. And if you give only the edges, that was even worse performance. So, what these researchers found out is that the ImageNet trained CNNs are biased towards texture. And so that means they they learn the texture very well and try to identify and try to classify images based on that. But if you increase the shape bias a little bit, like silhouette is the shape, but then it improves the results. But only based on texture, it does a very theoretically, within quotes, I would say, a very good job, 100% classification accuracy. But just looking at the texture here doesn't give us any idea about what animal is this about. So then in another study, what happened is it was found out that the models can actually recognize the race of different patients. So what they did is they did like for example, this is an interpretable map, saliency map that identifies the which is the important region here, informative region, and then they masked out this region, and then they trained the model again on the X-ray data sets. And what they found is interesting. In the original case, for you get very high performance numbers for different ethnicities, but when you mask it, the anatomical regions, then you kind of significantly degrade the performance, except for maybe this Caucasian race. But the idea is that it is learning because some races have, like people from certain parts of the world, they have different lung sizes depending upon their genetic makeup, bodily structure, and all that. So it is kind of learning those things, very race specific and all. So that is also another very important insight to have as to why we need to have.
There are many settings where a deep.
So this is just a short clip which just looks at how the different AI pioneers see the interpretability aspects. So let's have a look.
Model trained on enough data that exhibits enough accuracy on test data is all you really need to go, and you don't need to be able to see what's inside that black box. However, there are other settings where that's a very risky thing to do, even if you've got what looks like superhuman accuracy on the test data.
I resent right now that the neural net wave and deep learning wave has become so predominant that people say, well, that's the way to go. You just collect data and the intelligence will work itself out. And that's just not true. I don't believe it. If you just take existing data sets and you put them into a machine learning system, the machine learning system will just copy the behavior of that data set. And if there's biases and it's been collected in unfair ways, then that will be replicated in the machine learning system and probably augmented because the machine learning system will be used over and over again. The initial bias will get replicated. How do you fix that? How do you think about that? What are the legal issues that are involved there?
You just won't know about these problems. You wouldn't have anticipated them in advance if you can't sort of open up your model and see what's happening.
I think if we want to tackle some very complex problem, that kind of interpretability is necessary.
There's some AI people that say, look, it's a black box. It doesn't want to test that. Why do you need anything else? I just don't agree with that. I think this is a multi-stakeholder thing with many people that need to understand and all participate in their roles. And I think explanations is critical.
Now, I'm okay using technologies I don't understand. I got here on an airplane and I don't fully understand how airplanes work. But I take comfort knowing that there is an entire field of aeronautics dedicated to creating that understanding. I would like to live in a society whose systems are built on top of verifiable, rigorous, thorough knowledge.
And we just find that every time we put on this magic glasses where we can see what's inside the model, we find an amazing number of things that are wonderful, but we also see things that are very surprising, very disturbing, and that no human would ever let get deployed until they found a way to fix it. And it's just so important to be able to put on the magic glasses in many domains. There are many settings.
Okay, so basically that was something really, although it was a bit, old, you would say, 7, 8 years earlier, but this basically sets this foundation or the stage for why interpretability is necessary and why we should not overlook it, particularly in the present context when the first one of the speakers said, Professor Jordan said that we just can't, through data and expect that the neural network will learn. And now if you follow the opinion of Professor Jan Le Kun, he is, in fact, he was there at one of the but one of the delegates there sitting at the side. So now his opinion is that we need to take our focus away from LLMs if we want to build really highly intelligent systems. So all these things, all these insights are possible only when we are able to get into the system, get into the model, understand how it works and all. So before I go forward, just want to refresh a bit of the terms, what it means. Basically, black box operation methods is you no need to have access to internal models. White box refers to there is access to the gradients or whatever internal weights of the model, and outputs can be in terms of visualization, saliency maps, concepts like a summary statement, or feature importance, like you see in random forest or decision trees, how important each feature is. Now we will look at mostly into what we call the saliency maps. And there's a very interesting quote by Christoph Molnar that says these explanation algorithms are like yogurts in a supermarket. You have so many of them, you don't know which one to use and which one to start with. And that's actually a fact. So let's go into that then. Interpretable DL. So this is the structure of a CNN. There is convolution layers, pooling, subsampling, fully connected layers, finally output predictions. And we kind of know that the earlier layers learn the low level features like, the edges, and the different the texture, not the texture, sorry, the different the low level component like edges, and then mid level features are a combination of those texture and shape. High level features are mostly global features that help in like shape and orientation and all these things. And then that can go into like you can find prototype class members for different classes. For example, here this is goose, non-goose. So you have, because the training data set had images of goose in different set poses, different positions. So you get these template vectors, or you can say prototype class members. The same to do with other things like whether it's bell pepper or husky, lemon, whatever. And if you were to do this back propagation and try to find out which region was important, then you find something like this. Okay, this is a region, and this monkey and this tractor or whatever. And then, so what happened is once this was identified, so then people started looking at, can we synthesize the preferred inputs of the neuron so that we can get a desired kind of output. So they started using the generative models. Not so actually generative models are not new. Right now, generative AI is the trend, but those have been built on a lot of, like, starting from variational autoencoders to GANs and all the things, then transformer architectures, etc. So basically, you kind of try to synthesize certain inputs, and here you are able to get these. These are actually synthetic images for using gradient and back propagation and all the generative networks. So what they're able to, so basically the message from this picture is that the prototypes that were learned by the networks and the generative models, they were actually really good. The prototypes were really fairly accurate, and generative models did a very good job of reconstructing that. So that was kind of a good step forward. And then there was another type of model called the model agnostic explanation. It's called local interpretable model agnostic. There, what you do is you take original image, determine the probability, then mask certain regions or make some changes, perturbations, like adding noise and etc. And you see what is the outcome. So what it was found is, like, here, if you occlude the background, but still expose the essential parts like the eye and all, the performance improves. Like the probability goes from 0.54 to 0.85. But if you occlude the eyes, you go to a very low probability. But if you occlude just the background, it gives more or less the similar numbers. So what this tells us is there can be the first important conclusion is that if you are focusing only on the important parts, the most informative parts, then you can train models with better performance. Okay, so that is how, if you are focusing on this region. The other takeaway message is that if you have a lot of background, like unnecessary, irrelevant information, like here, for example, the background here, you don't learn a lot of. You tend to learn uh, noisy numbers, like the performance is hampered quite a lot. So these two conclusions will be the basis of something interesting that I will show later on as well. So these grad camps started coming up where you are able to highlight the most important regions that the neural network identifies. Then there were variations of grad camp, refined, more accurate versions and all. And again, there were other methods like you do different kind of perturbations, noise or blurring. Are you able to are they robust in the sense that the activation maps, are they robust to these kinds of noise? And so the idea was to see which one would be a good way to get. And in fact, the one of the very common application of these grad camps is you can actually do segmentation in an unsupervised way. And I guess, see, for example, here, if you get this mask, you can do a localization first, and then segment this region, the cup region and all, without even if you don't have pixel level annotations to train a unit or anything like a transformer model or anything. So then again, there was this LRP, or layer wise relevance propagation. It looked at different layers of the neural network, which one was more robust and all. And these guys from Google, they and UC Berkeley, they published this paper for sanity checks for saliency maps. Like they compared the all the current at that point of time contemporary maps, methods to get saliency maps, and they found out, they came up with these outputs, and they show that how, which they do analysis, which type of saliency map generators are good for different scenarios. And then, yeah, this may similarly from different layers, like 7 layer, 6 layer, 5 layer, layer number 5 and all. So now the question comes is, okay, that's great, but is there any use beyond just visualization? The answer is yes. Now, if you go back to what I mentioned, that the two conclusions, that background in uninformative background degrades model performance, and second, if you focus on the informative regions, you get a better model performance. So that understanding was used by was started to be used by different researchers. So basically, you have an input and the corresponding saliency maps. It can be seen as a fingerprint, like the most important information concentrated on in specific regions. And the researchers started using it for image retrieval. So then they actually did a very good job of doing image retrieval compared to using the actual original images. And so they were able to do quite good. And then some of the work was to, in neuro-oncology, for example, where would you do segmentation and all? If you include saliency, without saliency maps, you have these lot of these spurious regions. But if you do this focus on saliency maps, then you can identify these exact regions of disease activity. And then similarly, the low and high grade gliomas and all these things. So people started doing this, and a model entered shortcut learning. So it was able to focus on these important regions. Now, so even I have worked on these aspects using interpretable maps. So one of the first works that I did was around. Just hold on. So one of the first works was to use it for active learning and zero shot learning. And there I looked at how, when we add more and more samples, how the saliency maps change. And this says that, yeah, as you add, obviously, as you see more informative samples, you get a more clear picture of what the important regions are. And then I put it together in a pipeline to do, do active learning, which is basically selecting most informative samples for classification. And here we found that if we use informative sample selection, then we are able to do better than fully supervised models, like without sample selection, which is this blue horizontal line. And so the green one is the interpretability approach. And you surpass the performance of the supervised model at much lesser data, which is basically here, which corresponds to something like 37%. And that would depend also, this threshold would depend on the data set, but the idea is similar for all cases, is that with informative sample selection, you can actually do better. And that is something also being emphasized by Professor Andrew Ng over the last many years, that good quality data is better than having a lot of noisy labels without any data cleaning and all that. And so how do experts perceive this whole interpretable AI thing? So the way to look at it is, so there was a survey done from different like clinicians with different clinical background. And this is basically some of the statistics of their age and the years of experience. So they were asked some questions. So the first question they were asked is, Do you think interpretability or explainability methods are a must in for AI? Or like for AI methods, this most of them said yes, majority, and this survey was little old, but again, I think if you ask them now, it's probably it will change significantly. Um, then again, what kind of information do you want from interpretability methods, etc.? Which aspect of interpretability is more critical for you, like safety and efficacy, trustworthiness, and to audit ability to audit what AI system does. Basically, audit means to be able to get into and try to understand how it works and all that. So to wrap up the interpretability part, that although the interpretability is not a new concept, but because of the rapid advances in AI, so there has been a lot of effort going on to understand the whole different AI systems better. And when we talk about interpretability, we don't intend to have every part, have understanding of every component of the system, but we need to have enough information to fulfill the task that we have been assigned. And it can you can understand working of a smart system better. Visualization helps in improving trust, and benchmarking is still an ongoing area actually. So now I'll go to the next step of my talk, which is about active learning with foundation models for medical image classification. So initially, I showed you earlier that there is active learning can be used with saliency maps and all. So here we continue to use the saliency maps. But why foundation models? Because foundation models are probably the state of the art models right now, and you take any domain, if there is a foundation model available, then it definitely does better than any other method or any other model. But it has some limitations in the sense that it requires a lot of computational power, which means financial investment and also large annotated data sets. Then secondly, the models are inherently static, and you can't easily update it, particularly if it is being used by institutions or organizations who don't have a big budget for all these things. If you don't update, then it becomes an issue. And even if you have to use adapter based tuning, then still you need some supervised learning with label data. So the question that we want to answer is, how can we efficiently adapt black box models to new medical tasks with minimal label data and without accessing the model's internal parameters? So basically, then the other question, the second part also of the second problem here is, we also need to see where active learning can we look at incorporate active learning into the whole workflow, because active learning will help us to get good performance or optimum performance with fewer samples. So definitely which should be explored. But existing active learning methods do have, they assume that there is access to model parameters. They are not feasible for black box foundation model. So basically, black box foundation models, to reiterate, is something where you don't have access to the weights. This is particularly the case when you are interacting with the foundation model through an API or through a way where you cannot access the model weights and architecture and all that. So basically, we propose a method which we call as VAPL, which is the short for visual adaptation for prompt based active learning, and I'll show you how this works. And another important concept is this zoo, or zero order optimization, which is basically a way to have access to foundation models even if the weights are not accessible. So this is this is achieved by doing some perturbations, adding noise, and seeing how the level of noise influences the final outcome. So basically, the workflow that we have is that we have the original image, then say a slightly perturbed image encoders, prompt decoder. They go to the foundation model, and both of the original output and perturbed output, they are used to calculate unsupervised loss. through zero order approximation, and then finally it trains the visual prompt decoder. Zero order optimization basically means is if you have a, let's say, a loss function like unsupervised loss function, the parameters are theta, and you do a slight, when you calculate a gradient, you do this plus delta and then minus delta. So that's something that's exactly the concept. So you take a vector and some magnitude, like you can, let's call it a noise or a perturbation vector, add it to the parameters and see what is the output. Then subtract it and see what is the output. So you get now 2c, or the step size, which kind of is the a gradient, like in terms of first principle method. And the unsupervised loss function that we used to train the prompt decoder is something combining diversity, entropy, and the feature similarity. And these three serve different purposes. So so once the VIPD or the prompt decoder is trained, then you can rank informative samples in the VIP training. So here the role of interpretability is that it kind of is not explicitly encoded, like when we looked at CNNs, we looked at having saliency maps, then using those feature vectors, but it is kind of implicitly encoded in this process because of the different layers and visualization techniques. And if we apply them to different data sets, like these 4 data sets are chosen because of their large numbers, and there are benchmarking studies with that. So we found that if we are able to, like our VAPL is able to do better than the fully supervised and most of the other methods that with which we compared. This is on the Chexpert dataset, same for the Patch Chameleon dataset, as well as the ISIC, the Skin Lesion Challenge dataset. So basically, the key takeaways that I would say from this presentation or talk is that although the foundation models don't let us have access to their weights, but we can still train, like have an active learning framework to adapt these black box models. And we can so we made use of perturbation, which is a very simple mathematical operation to determine which models, I mean, to have a whole active learning setup. And then, to conclude, I would like to thank my all my collaborators from different institutes, like from Bern, Monash, RMIT, Geo Institute, EPFL, and of course, Mohammed bin Zayed University of AI. And basically, this brings me to the end of the talk. Thank you for your attention, and I'll be happy to take any questions.
Yeah, thank you so much, sir, for the nice presentation and have shown us the importance of interpretability in images as well as in medical imaging, how important it is, and also you have shown few techniques for that. So now I request the participants, if you have any query, then you can write your queries in the chat box.
Okay. Yeah. So there is one question already from Pooja Soni. Which explainable AI method to use for a scenario under consideration? How do we decide that, and how to interpret saliency maps to begin with? Okay, I'll answer the last question first. When we look at saliency maps, the regions that are highlighted are what the layer, what the model learns. So basically, wait, I'll share my screen to illustrate the point. Okay, so if you look at this particular look at this particular slide. Here, if you look, these are the different layers. So starting from first layer to the 7th layer, convolution layer, and you will see that different layers give slightly different outputs. And particularly if let's go to GradCam or something. So because we know that the initial layers will learn the low level features like texture, edges and all, while the later layers will learn the high level features like shape and other domain regions. So, so to answer your question, so what I would say is, if you have like, for example, how to understand or interpret is, the primary interpretation is that what is the informative region in this particular image that helps the model to learn whether to classify it as a particular class or not. And so to come to your first question is, um, how do we decide which XAI method? That actually, I would say, depends a lot, but that is a bit subjective. Um, but if you are working with images, then GradCam is probably a very good. But people have improved upon GradCam, and have given more compact representation. So if you look at layer 7, it will highlight a particular, maybe the shape, but if you look at layer 1, it will highlight a different region. So that would depend on that. So XAI method is like, it's like that example I showed of the yogurts in the supermarket. You have to first try and taste it to understand which works best for your purpose. So there is there is no universal rule. But I would generally go with the latest methods because they have improved upon the previous methods. Okay. Next question is from Suman Rekha, that can these XAI methods like Lime and SHAP be used for feature selection? Yes, in fact, they are very important. They can be definitely used for feature selection. You can understand that which regions are important, and for example, in the same is like which features are important. So if it's if it's an input is an image, you see which regions are important. So you can focus on those regions. But if it's like a number vector, then you find which features are important. So that's how you can do feature selection. Follow-up question is, if one is not a domain expert, how to go about segregating the identified features of the images from the saliency maps or GradCam outputs? Okay, let me try to understand the question.
Is not a domain.
Or GradCam output. Okay, so what I understand is, how do you understand the clinical relevance of the features? Clinical relevance is something that a domain expert can help. For example, as a image processing scientist, you can show the doctor that this is the region where the model finds it important. But what exactly is the actual relevance would depend upon the doctor. Because if it's a lung, he would see whether the size of the lung, or if there is some kind of diffusion or air blockage or something. So that is something you will learn with when you read and about the field and get that, and interact with the domain experts. So there is no there is no one single rule to analyze this. Okay. Any other questions?
Hmm. Sir, you are talking about, how these interpretability will help us in unsupervised segmentation.
Yes.
So if you can explain that a bit more on that.
Okay, sure. I'll again share my screen then, my presentation. Okay. Okay, so suppose, let's take this one. You have this image. You want to classify it as well as do the segmentation, segment the region, whatever, in this case, like a bird. So conventionally, if you want to train a unit like supervised segmentation, you need to have a lot of annotations or pixel level annotations and all, which you can use it to train. But if you don't have, then look at this GradCam, for example, this part, or any other thing, GradCam, uh, or guided backpropagation. So here it gives you the approximate region of the important object, right, or the informative object. So you can threshold it and get a bounding box here, right? So now let's say you got a bounding box around this bird, and now you can do, for example, k-means clustering, and or do some foreground background separation like a graph cut or something. Well, graph cut is again a supervised, okay, not graph cut, but you can do k-means clustering and to find out, okay, which are the different clusters. For example, this region will be a cluster, this region will be different clusters, and then you can do actually a segmentation. Or the other way is, if you get a bounding box here, you can initialize a classical segmentation approach called level sets, which is basically you would do an initial map and then iterate. It will gradually shrink or expand and segment out the whole bird. So I don't know if you are familiar with level sets or active contours, because I don't, because those are taught in classical computer vision methods, and I am not sure how popular it is among students right now. But it's always good to know these kind of classical methods so that you can do things depending upon the resources you have. Even if you don't have neural networks or GPUs to train, you can do this approach.
Thank you, sir. I don't think. Is there any other questions from the participant side?
There is one question. Okay, again from Pooja. Image datasets with multiple classes that are very similar. What extent XAI can differentiate between the given images? So that depends a lot on um, the particular domain, to be honest. If the fine grain, there is something called fine grain classification, then you have to look into that aspect, and it depends. They can help probably. Class, if you design the, if you tweak the loss function of the GradCam, it can give you more focused. It can give you the identify the variations in between images. So I can, yeah, I have done some work on that, and I can say for sure. Then with okay, question from Ram Singh is, majority of paper in image reconstruction and source results in MSc, PSNR, SSIM. However, medical images are of high ranges. What is the correct procedure to measure the high range medical images and CT and MRI quality in terms of MSc, PSNR, and SSIM, other than normalization method? Okay, the way to see it is, it's a bit difficult to, I mean, it's a bit difficult to have a very one answer that fits all, because if you have a high, some value of MSc or PSNR, you have to measure it relative to a certain step. For example, if before pre-processing you are getting this value, after pre-processing you are getting higher PSNR, then it means there is been an improvement. And if it is not a normalized value, like for example SSIM, it's a normalized value, so you can say something about whether it's improving or not. But if it, when it comes to classification or segmentation, dice metric scores, it's a normalized value. You can give some number. But when it comes to this quality, reconstruction, restoration, depends upon the metric. PSNR higher is better, MSc lower is better. So, but it always has to be with respect to a reference. So just a number 32 dB of 0.5 dB PSNR has no meaning. We can't say, unless, you know, there has been studies that see that, okay, X-rays, a good quality X-ray means this much PSNR values and all. So yeah, without those reference values, we can't make any claims. Anything else? No, right? Or
No, I couldn't see any other questions in the chat box. I think. Okay, so I think, sir, there are no other questions from the participants.
Yeah.
So if they have, they can drop an email to you maybe later on. Yeah.
Yeah, sure. Yeah, that would be good.
Mhm.
Yeah.
Yeah. So thank you so much, sir, for joining us today and sharing your insights and interpretability, active learning, and how they can be applied on the medical images, and how they improve the performance, and how they also improve the trust of the end users, basically the doctors and the clinicians. So thank you so
Yes.
much once again, sir, for joining us. And I think you are also having another talk in our FDP, which is related
Yes.
to image analysis in low data scenario. So we look
Yes.
forward to that talk, sir, on
Yeah.
9th May, Friday.
Yes. Yes. 9th Friday. Yes. Right.
Yeah. So thank you so much once again, sir.
No problem. It was a pleasure. Thank you, Deepak, for inviting me to be part of this program. People did benefit from my presentation.
Yeah. Yeah. Thank you, sir.
Thank you.
Yeah. So participants, that's all for today. I think there are only two lectures. I hope you have at least got some idea